All right, today we are starting chapter 8. Section 8.1 is about ratio and proportion. And I'm sure you've seen ratio and proportion before now. A ratio is a quotient of two numbers, and it's always written in lowest terms. So a ratio we usually write as a fraction. Remember, a fraction is a way to write a quotient or a division problem, and it's always in lowest terms. So an example of a ratio of 5 meters to 3 meters can be written like this, or like this, or like this. But yes, the fraction is best. The fraction is best because we naturally will simplify a fraction. We don't always tend to simplify when we write it in the other forms. The slope of a line is a ratio between the rise to the run. Remember, we define slope to be rise over run. And if you remember, that equation was y2 minus y1. That's the change in the y values, the rise, over x2 minus x1, the change in the run. You may need that later, hint, hint. And on a map, scale is the ratio between the map distance and actual distance. So this scale here says 1 centimeter on the map is equal to 30 miles in real life. And so we can use that scale to find measures between, say, cities on a map, actual measures. So a ratio is one fraction. It is one fraction that it's a ratio of two numbers, where a proportion is an equation setting two ratios equal to each other. So it looks something like this. I'm going to make this, well, I'm not going to make it bigger, but it looks like this, a proportion. And in this section, we're going to take note of every position in that proportion. In other words, we're going to call A here, the top number in the first fraction, the first term. B is the second term. C is the third term. And D is the fourth term. And the reason I underline those specific colors is because the first and fourth terms are called the extremes, and the second and third terms are called the means. So the means and the extremes are what we refer to them as. And so if you see that, that's what it means, okay? So let's go to this first theorem. So in a proportion, the product of the means is equal to the product of the streams. We call this cross multiplying, or I usually call it the cross product. So again, you should have learned this before, but we're reviewing it. A times D equals B times C. A times D equals B times C. And so in any proportion, that cross product is always true. They're always equal to each other. And oops, I could illustrate it just by something that we already know. We know 2/3 equals 4/6. If we multiply the top and bottom of the first fraction by 2, we get 4/6. But notice when we look at the cross product, 2 times 6 is equal to 4 times 3. They both equal 12. So that cross product is always true for any proportion. Next, we have if the product of a pair of non-zero numbers is equal to the product of another pair of non-zero numbers, then either pair of numbers may be made the extremes and the other pair the means of a proportion. In other words, if you have something that looks like this, you can always write it to look like something like this. If we take that AD equals BC, well, we can divide both sides by D, and that gives us A equals BC over D. And then we can divide both sides by B, and get our final A over B, these cancel out, equals C over D. So we can always convert that product of pair of non-zero numbers to the product of another pair of non-zero numbers to equal a proportion. All right, so now the geometric mean. The geometric mean, if the means in a proportion are equal, then either mean is called the geometric mean or mean proportional. Okay, these are interchangeable. And so notice the x's are equal here. See, the x's are the same. So in other words, what we get is x squared equals a times d. And so the x is the geometric mean, okay? That they're equal, and solving for x, basically x is going to equal the square root of a times d. So let's look at some examples. First of all, I don't want you to miss this. The arithmetic mean is the normal average, right? So when we say average, like a bowling average or calculating the average, that means that's normal. That's the arithmetic mean. So the geometric mean is what we just talked about up here. The x squared equals a times d. So let's, well, this example is done. Let's just look through it. Find the geometric, both geometric and arithmetic means between 3 and 27. So normal average, 3 plus 27 divided by 2, 15. That's the arithmetic mean. Geometric mean is we're going to set up this proportion, right? 3 and 27 on the extremes, x in the means. And so we get x squared equals 81, or x equals plus or minus 9. Now notice we have plus or minus 9 now, because when we consider when x squared equals 81, if we plug in 9 squared is 81, and also negative 9 squared is 81. Another way to look at this is if we took that x squared equals 81 and we subtracted 81 from both sides to get x squared minus 81 equals 0, and we factored it, we would get x plus 9, x minus 9, and still answers of 9 and negative 9. Notice you can write it with the plus or minus. And so the geometric mean will have two answers, the positive and the negative. All right, so other problems you might encounter are like this here, solve for x. So to solve for x, we are going to do the cross product. So 14 times 3 is equal to, that's times, is equal to 7 times x. Well, where do I have it? Oh, 14 times 3 is 42. Oops, 2. 42 is equal to 7x. Dividing both sides by 7, we get 6 equals x. Done. Find the fourth term of a proportion if the first three terms are 3, 4, and 5. So remember, it goes 1, 2, 3, 4, right? Those are the positions. So we're going to have 3 over 4 equals 5 over x. That's what we're going to set up here. These are the positions. So cross product here, we get 3x equals 20. X equals 20 thirds. And we're going to leave it like that. There's no decimal approximation. If it's a repeating decimal, we're going to leave it in terms of the fraction. Next, find the mean proportional. Remember, this is the same as geometric mean between 4 and 16. So we're going to set up our proportion. 4, 16, x, x. That's how we do the geometric mean. So 4 times 16, 64 is equal to x times x, or x squared. Square rooting both sides, we get x is equal to plus or minus 8. Our next example is find the ratio of x to y. So what we want to know is this, x over y equals what? Okay, so find the ratio of x to y. So we're going to take that 5x equals 6y, and we want it to say x over y on the one side. So we're going to divide both sides by 5. And we get x equals 6y over 5, and then we're going to divide both sides by y. And we get x over y equals 6 over 5. If you want to do that all in one step, do it all in one step. And finally, oh, not finally, we got a little bit more. Is this equivalent to this? Well, we're going to start with this and see if we can simplify it to be the other. So let's see. X minus 2y over y is equal to a minus 2b over b. Well, let's do the cross product. I'm going to move it over here. X minus 2y times b equal to y times a minus 2b. Distributing. Bx minus 2by equals ay minus 2by. Well, if we add 2by to both sides, those are the same. They are going to cancel out. So that leaves us with bx is equal to ay. Now we want a over b, so let's put a over b and get rid of the y's at the same time, and we get x over y equals a over b. Looks like they match, yes. Finally, because we have, we're going to be taking the square root to solve for the geometric mean, I want to just review how to simplify radical forms. In other words, if you had to simplify this, the square root of 20, that is not a perfect square. And so how I do it is I do a factor tree. So I do the factor tree, so 20 is equal to 2 times 2 times 5. Now, we know anytime you have a number times itself, that's a perfect square, like 2 times 2 is 4. So any pairs can come out, so the 2 comes out, that's a perfect square, and the 5 stays in. So some teachers do it like this. Right? And that gives us 2 square root of 5. You might like that, but I find as the numbers get bigger, it's hard to always find that perfect square. By doing the factor tree and taking the pairs out is a lot easier and friendlier. Let's try another one, square root of 48. So 6 times 8, 2 times 3, 2 times 4, 2 times 2. So just so we don't lose anything, I'm going to circle all my factors. So pairs, pair of 2's, another pair of 2's. So 2 times 2 comes out. That 3 stays in. So 4 square root of 3. Again, if you did it the other way, you would have taken this. But it's not always easy to find that 16 as a factor. When I see 48, I think 6 times 8, and that's a lot easier. Finally, one more example, the square root of 108. Again, I look at that and I'm like, well, I think 2 goes into it, maybe 4 goes into it. I don't know if I necessarily know the perfect square. Well, let's see. That's 4 times 27, 2 times 2, 3 times 9. Oops, not 9. Circle the 3, and 3 times 3. So a pair of 2's comes out, a pair of 3's come out, and that 3 stays inside. So 6 square root of 3. Otherwise, if you did it the other method, you would have had to come up with this. And I don't know, but I don't know my multiples of 36. That's a lot harder. So I encourage you to try my factor tree method.